Our topics today are going to cover what the spatial index is and its purpose when working with ArcSDE, how the spatial index works, which will look at the architecture of the spatial index table, as well as exactly how the RDBMS and ArcSDE use the spatial index to resolve spatial queries. Once we have a thorough understanding of how the spatial index works, we're going to look at ways that we can choose a spatial index size if you don't want to accept the default parameters that are generated by the ArcGIS application. We'll also look at tuning your existing spatial indexes or changing the spatial index value if the data that you're working with changes. So ways that you can look at trying to squeeze out some better performance for your spatial queries. Now, the format of this seminar, we're going to have each of these topics, there are sort of three groupings of topics in all, followed by a brief question and answer period. So we're going to start by looking at the basics of indexes, because spatial indexes and regular RDBMS indexes kind of behave in similar ways and are used for similar reasons. We use an index so that we can search for a value in a table without having to read the entire column. So this allows us to perform queries much more efficiently. If we don't have indexes built against a table and we want to find matching values, we have to scan every value to make sure that we're not missing any. There are two different types of indexes, and this has to do with the way that indexes are structured in the database and how they're structured and stored. Probably the most common type of index, and we've probably all worked with them in one way or another, maybe without even realizing it, is to have a table that stores your data and the index as a separate object. So when you perform a query searching for a value, the query looks at the index, and the index will point them to the location of the actual row of data in the table. An example of this would be using a textbook that had an index at the back of it. So your textbook may be ordered in a particular way, various topics and various chapters, but you can go to the back of the book to the index, which is separate from the rest of the textbook, and look up particular keywords. And associated with each of those keywords would be a page or a list of pages where you might find more information on that topic. So instead of having to scan through the entire book, you can look in the index and find exactly what you're looking for a lot faster. The other type of index is one where the index and the table are sort of the same thing. That's when your table is sorted or stored in the order of the index. An example of this would be a phone book or an encyclopedia. Unlike a book index, in a phone book, everything is stored in the order of the index. You don't have to go to a separate part of the phone book to look up the name and then visit a different page to find the phone number. Instead, everything is stored together, and it's in alphabetical order. So you know that if you're looking for a name that starts with T, that you'd go towards the back of the phone book where the letter T is located in the alphabet. Now, indexes, because they are stored in some sort of order, it's based on the type of data that the index is built against. And this is usually numeric or alphabetic data. So we have character data that would be sorted in index order from A to Z or the opposite order. Numeric can be ascending or descending against numeric type data. Now, in addition to the index itself, most RDBMSs also store statistics about the index. And what the statistics are is just information about the distribution of the data across the index. So the range of values, how many unique values you have, how many non-unique values you have. This enables the RDBMS to know more about what your data looks like, so that when you perform a query, the RDBMS can consult the statistics to determine the best way to resolve your query, rather than having to read through all of your data to figure out the best path to get to the values that you're looking for. This information is used by some kind of query optimizer. Sometimes your tables may have several different indexes. There might be several different ways that the RDBMS can get to your data. And you'd probably like to find the fastest way to get to your data, and index statistics are going to help the RDBMS figure this out without having to read all of the data to start out with. Now, these are regular indexes, but conceptually, they're very similar to spatial indexes. We use spatial indexes for the same purpose. We want to be able to find our shapes quickly without having to read the entire spatial column or all of the spatial data before we find the shapes that we're looking for. So in this way, a spatial index is used for efficient spatial searching. The difference with a spatial index is that we're concerned with searching shapes rather than attribute information. What the spatial index does is use the envelope or bounding box of features for faster searching. Now, every feature has a set of coordinates that represent the smallest box you could draw around the feature and enclose all of the geometry of that feature. So this is known as the feature envelope. And within ArcSDE, we're able to maintain information about the feature envelope for every single shape. So polygon features, line features, point features, they all have envelopes. The envelopes may look a little bit different when you compare them to the shape of the feature. For example, a point doesn't really have any area, and so its envelope is actually the same coordinates of a point. The envelope of a polygon may look a lot like that polygon, may sort of represent something very close to the area that's taken up by that polygon. Line features, lines themselves don't have area, but they can span distances. And so the bounding box would contain the minimum and maximum coordinates of that line. Now, I'd like to remind everybody to type their questions into the question and answer box. I only see a couple of questions up there right now, so if you have questions, just feel free to type them in at any time. Now, the same way that there are different types of regular column indexes, there are also different ways of constructing a spatial index. And ArcSDE makes use of two different types of spatial indexes. Now, these are really based on the type of RDBMS software that you are working with. What we're going to be looking at in this presentation specifically is what we call the grid tile index. And this is the kind of spatial index that's used by IBM's DB2 RDBMS, Oracle, and SQL Server. The other type of spatial index is used by Informix and Oracle Spatial, and it's called an R-tree index. Now, we're not really going to talk about the R-tree index much in this presentation simply because it's managed by the RDBMS software. So it's important that this index gets built, but the user doesn't really have to be involved in its creation, doesn't have to make any decisions. It's all maintained and built entirely by the RDBMS software. So it's one less thing you have to think about if that's the kind of database software that you're using. If you're using DB2, Oracle, or SQL Server with ArcSDE, you'll be using a grid tile index. A grid tile index is a separate table that is searched with range queries. So it's a little bit like consulting the index on a street map to help you locate a street, rather than having to scan the entire street map to find a street. You're able to go to the index, and it points you to just a small part of the entire map that you can scan to find the street that you're looking for. This is exactly what the grid tile index does. In the same way that your street map index has a grid over top of it, and you go to individual grid squares to look for your streets, the same thing happens with the grid tile index. You, as the user who loads or creates your data, controls the size of those index tiles. So that's what we're going to be talking about in the next part of the presentation, is how those tiles get used by ArcSDE and by the RDBMS to resolve your spatial queries, and ways that you can go about choosing an appropriate size for your spatial index. So to recap quickly, we've looked at what a spatial index is and the different types of spatial indexes. And what we're going to be examining in more detail in the next couple of sections is the grid tile index that's used by DB2, Oracle, and SQL Server for ArcSDE. So if anybody has questions, please type them into the question and answer window. In this section, we cover the basics of indexes, why we use them, the different types of spatial and regular indexes. And in the next section, we're going to be looking a little bit more closely at the index architecture and how the grid tile index is used. Right now, I'm going to let Michael take the first question for me.
We have a series of questions here that are asking about R-tree indexes with Oracle specifically. The first one asks, the R in R-tree stands for what? R in this case means range, and the range in this case is the envelope of the feature, and the feature covers a range of coordinates in the x direction, a range of coordinates in the y direction, hence the term R-tree. We have another question that's asking if you're using Oracle Spatial, should you use an R-tree index or grid tiles? And the answer is that the type of spatial index you use is determined by the underlying format of your data. In this case, with Oracle Spatial, you in fact have two different types of indexes that are supported by the Oracle Spatial software, one of which is an R-tree, one of which is a type of specialized grid tile index called a quad tree. And for more information on that, you can refer to the Oracle Spatial User's Guide and reference. The last question we have here is from Gregory in New York, and he's asking if you're using Oracle Spatial with an R-tree index, do you not need another index in SDE? The answer is yes, you don't need another index because SDE will use the underlying Oracle Spatial index.
Okay, let's see. We've got a few more questions coming in here. We've got a question from Charles in Hawaii. Is spatial index related to the spatial domain? No, it isn't really related to the spatial domain. The spatial domain and the spatial index are something that you can specify when you create or load data, but the spatial index is really there to make your spatial queries more efficient, and you can modify the values that you've set for spatial index at any time. The spatial domain controls the level of accuracy that you can store for your data, and it also controls the extent of space within the geodatabase that you have to store your data set and enter new data in. And the spatial domain isn't a value that you can modify once you've created a data set, but they are both things that you specify when you create or import data. Michael, take one more question.
Okay. We have a question from Sue from Idaho that's asking, is it better to have a fast machine with a bad index or a slow machine with a good index? This is kind of a difficult one to answer, and it really depends on the type of data you're working with and the relative difference between your CPU and your hard disk. But as a general statement, one of the things that indexes do is to reduce the amount of physical I/O between the CPU and the hard disks. And keep in mind that your hard disks are going to be several orders of magnitude slower than accessing data in a CPU cache or accessing data from RAM. So in general, I would just say that it's a tough call, but it's probably better to have the good index because it will be reducing that disk I/O, which is one of the slowest parts of your server system.
Okay, I'm going to take one more question before we move on to the next section. We have a question from Joan. It says, is there ever a case where a default spatial index would not get created? And that's a good question because, and we'll look at this later on in the presentation, the default settings are not always appropriate for your data. And the computer that sets those defaults doesn't always know what your intentions are. For an example, if you create a brand new empty feature class, the default we'll look at later on is 1,000 of your data units. And if you try and load a really enormous feature that is several times larger than that 1,000 grid tile size index, it might actually refuse to load that piece of data. So the spatial index is always going to be created, but you may not actually be able to use it for your data. So you'll always specify a value, and ArcSDE will attempt to build a spatial index based on that value. But there are times when the spatial index value is really inappropriate for the data that you are loading. And often with the default settings, the computer has no way of knowing what you mean to do with the data. And what we're going to try and help everybody with in the rest of this presentation is to gain a better understanding of exactly what the spatial index is doing, what the default settings are, and how you can go about picking settings so that you avoid situations where a default spatial index wouldn't get created. Okay, so thank you for those questions, and we're going to move on to the second section now, which is looking at the architecture of the grid tile spatial index and how the grid tile spatial index works. So in this and the next slide, we're going to take a closer look at columns that make up the spatial index table. Now, I mentioned earlier that the spatial index table is a separate structure. It's a separate table that is exactly like having a street map index associated with a street map. So with every feature class, you have an associated spatial index table. And in that table, you have 7 different columns. And we're going to step through what is contained in each of those columns. So if you look at the example on the upper half of this slide here, we've got a set of features. Those are the gray shapes. And we've got grid tiles that are laying over top of them. Those are the red squares. Every grid tile has 2 identifiers, an identifier on the x-axis and an identifier on the y-axis. And this number, it's just an integer, is stored in 2 index columns, gx and gy. So these are the grid tile values themselves. Now if you look on the bottom half of the screen, you'll see the next set of values that are stored make up the shape envelope of each shape in your feature class. So what's being stored in this table is a combination of each grid tile and each shape envelope that crosses into that grid tile. So whereas you may have one shape and one set of attributes of that shape, if that particular shape's envelope crosses multiple tiles, you may have multiple records that refer to that particular feature. So this is 2 coordinates, or 4 actual numbers, the minimum x and y and the maximum x and y for each shape's envelopes. So that makes up the next 4 columns in our spatial index table. I'm going to take a quick little break here and ask a polling question. I'm kind of interested to find out of everyone who's listening to this presentation, which of you are database administrators and which of you are more the end user or the GIS person involved. Because I'm kind of trying to see where the audience is, or the background of the audience members. So if you are a DBA or you're responsible for administrating the database that houses ArcSDE, click yes in the polling window. And if that's not your role, click no. And we'll review the results of this poll in a couple of slides. So moving on with the rest of the grid tile spatial index architecture, I mentioned that there's 7 columns. So the first 6 were the grid tile identifiers and the individual shape envelopes. And the very last column represents the geometry. It's actually a feature identifier, or an ID, that will link each record in the spatial index table to its corresponding shape that's stored elsewhere in the database. So we've got the grid tiles, the shape envelopes, and then the very last column is the shape itself. The last thing we're interested in finding here is the actual shape. What we want to be able to do is use the grid tile and the envelopes to remove as many records from our query results as possible. What we'll pass on to ArcSDE to evaluate further is the shape itself, and we'll see how that works in the next couple of slides. So this is the contents of the spatial index table. We've got these 7 columns. They all contain integer values, so it's extremely rapid for the RDBMS software to search through these values. As well, we have a large covering index across all 7 columns. And the spatial index table is really the first stop for any spatial query. So any kind of query that's returning a subset of all of the features in your feature class is going to stop first at the spatial index table and see if it can reduce the number of shapes that ArcSDE needs to look at directly. The same way that when you're using a map index, you'd rather find values in the index and search a small grid tile than have to read through every record on your street map looking for the right street. Now, to take a look at the results of our survey today, we've got 38% of you say yes, you're in the database administrator role, and 62% of you say no. This kind of topic, dealing with ArcSDE in the spatial index, is something that can transfer between the database administrator role as well as the person who's doing the GIS work. But just to let you know that if you have other people that you're working with in your organization as database administrators who are going to be working with this, we have one more workshop this afternoon at 3 o'clock Pacific time that they may want to participate in. Okay, now we're going to be looking at how the grid tile spatial index works. So we've seen what the contents of the spatial index table are. Now we're going to see how the RDBMS and ArcSDE work towards the goal of avoiding having to read features for the entire feature class. So we're trying to eliminate the number of features that we have to look at directly so that ArcSDE has to do a little bit less work. In the example that we're going to be using here, we have a parcel feature class, those are the gray features, and we've got a spatial query filter shape. Now when you execute a spatial query, there are always going to be three parts that you're looking at. The data that you're querying, that you want to get results from, and then some kind of shape that represents your spatial where clause, and then the relationship between them. So in this example, we want to find all of the gray shapes that intersect the blue shape. Now that blue shape could be a selection from another feature class, it could be a graphic we've drawn on the screen, it could be a zoom window that we've delineated. Any shape like that, that's going to represent our spatial query filter. Now there are 4 stages of elimination that take place to reduce our data sets. And 2 of those stages are done at the RDBMS level. 2 of those 4 stages are done by the ArcSDE level. So for the next couple of slides, that's what we're going to be examining, are those 4 stages of elimination. So the first couple of stages, like I said, this is the primary filter, if you will. It's handled by the RDBMS. So this takes place always on the server, directly within the database. What ArcSDE is doing is determining ahead of time which grid tiles that spatial query filter, so the blue shape, are crossing. When it knows the IDs of those grid tiles, it formulates a query for the database that says, find all of these records in the spatial index table that have the same matching grid tile IDs. So this is a grid tile and grid tile search. We find the grid tile that the spatial query filter hits. Then we want to go find the corresponding grid tile records from the spatial index table. So you can see in the top half of the slide, the yellow records are the ones that are thrown out by this level of query. The green records are the ones that get passed into the next stage of the query. So these are the shapes that fall, their envelopes fall some way into the same grid tiles that are crossed by the spatial query filter. Now, if this data set could be much, much larger than just the piece that we're looking at. So this is probably the greatest stage of elimination is taking place with this very first stage. That's when we zero right in on just the grid tiles that we're interested in looking at closer, and we ignore all the rest of the features. Now, the second level of this spatial query, this is when we take a look at the feature that get passed from the first query down to the next level, and that is an envelope on envelope query. Now, just to clarify, because I don't think I've actually gone over this terminology yet, RDBMS stands for Relational Database Management Software. It's a similar term to that of just using database, but database was a little bit broad. This is actually the software that manages all the queries and retrieving and storing data within your database. So back to the envelope on envelope query. With the results that came from that first process of elimination, we then took a look at the envelope of the spatial filter and the envelope of all of those features that fell in those grid tiles. And again, we're throwing out the yellow features because their envelopes don't intersect the envelope of the spatial filter. So these two queries are done at database level, and they're quite quick. The next piece of information, so those green shapes down the bottom on the envelope on envelope query, those are the ones that get sent to ArcSDE for ArcSDE to evaluate in the next two stages. So ideally, the largest number of features get thrown away on that very first pass. And this is where the size of your spatial index tiles influences the speed with which this information gets passed through to ArcSDE. Now, I just want to remind everybody to type questions in as they get them, and we'll try to determine as many of them for answering as we can in the next section, but you don't have to wait until we have a question and answer period. Just type those questions in as you have them. So the second stage of our query, this is the last two processes of elimination to just return a result set. These take place with the ArcSDE server. If you are using a direct connect connection rather than an application server connection, so you're connecting directly from ArcCatalog, ArcMap, or some client application through to SQL Server Oracle, this stage takes place on the client machine. Otherwise, if you're using a regular ArcSDE application server connection, these two pieces still take place on the server, but it's ArcSDE that manages this part. And the database has done its part of the job, and it's passed to ArcSDE just the features whose envelopes intersect the envelope of our spatial query. Now, if you look at this slide, there doesn't seem to be a whole lot of difference between the last two stages here. Stage number 3, we're going to look at the query filter shape, so not the envelope anymore, just the shape, against the envelope of our features that got passed from the database. So all of those green features, we're going to look at their envelopes, and we're going to filter out those that don't intersect with the shape of our query filter. So that yellow shape up in the corner, it intersected the envelope. Their envelope's touched, but its envelope doesn't actually come anywhere near the shape of the query filter itself. So the very last and final stage is probably the most intensive amount of work, and that is looking at the shape of the query filter against the shape of the remaining features. And that yellow one down at the bottom, even though its envelope intersected shape, its shape doesn't actually touch the query filter, so it's the last one to be eliminated. These two are pretty similar, and we're getting right down to features that come very close to intersecting that shape, but they don't quite get there. So again, these two stages are done at the ArcSDE level. So just to recap, we have 4 stages of elimination. We've got the grid tile on grid tile and the envelope on envelope, which are dealt with at the database level. That's a series of queries that take place against the spatial index table. The results of those 2 queries are passed on to the ArcSDE server or to the Direct Connect client, and they filter out shape on envelope and shape on shape parts of the query. So just to review that last topic, we looked at the spatial index table schema, how that table is stored, what's stored in that table. We've also looked at how the spatial index works and how we eliminate features using the spatial index so that we don't have to scan through all the shapes themselves. So I'm going to let Michael take this next question for you.
Okay, we have a question here from Rugli, who is asking, is it true that all SDE commands, such as shape to SDE, use spatial index parameters for the SDE grid tile index? And the answer is no. Well, depending on how you ask the question, perhaps the answer is yes. Let me explain. If you have an SDE window available or a command window on a machine that has SDE installed, you can just type in any of these commands like shape2SDE, for example, to get a usage. And if you look at the usage for the spatial index parameters, you'll see that indeed there are parameters that accommodate the grid tile spatial index, but you'll also see one called artree, one called fixed, and one called hybrid. And these are used to set the artree index, and the fixed and hybrid are specialized indexes for the Oracle spatial format. So you can use shape2SDE to create a grid tile index, and you can also use it to create other types of indexes like an artree.
Okay, thank you, Michael. We have a question here from Kyle. Said the filter example is on one feature class. What happens when your selectable layers are set to many layers? This is a really good question. Each layer is going to be treated independently. So if I am trying to select features from multiple layers, and a good example of this would be having many layers open up within ArcMap and then zooming in to a smaller part of the map. I am going to be querying multiple data sets. So each of those queries will be submitted separately, one by one, through to the database. Each of those spatial index tables will be queried. The only thing that happens in common is that the one thing that we're passing in common is the spatial query filter will be the same, but the rest of the queries are handled on a feature class by feature class basis. And this is very similar to a question we had from Greg that asks if the query filter in a feature is a feature in a separate feature class, does this process work if the two feature classes have different spatial index sizes? Yes, every feature class can have a different spatial index size, and you should be sizing your spatial index appropriate to each individual feature class rather than giving everything the same spatial index. Because each of these are completed as separate queries, they're using each specific feature class's own spatial index. And I'll let Michael take the next question.
Okay, we have a question here from Michael who's asking, since a feature may be referenced multiple times in an S table, will it not always have the same envelope values? And therefore, why store all four values in each row of an S table? Isn't this inefficient? That's an excellent question. If any of you out there used SDE3 in the past, you may recall that SDE3 only stored the grid tiles in the index on the spatial index table. And in answer to another question, the name of the table that stores the spatial index entries is the letter S followed by a unique integer identifier number. So the index on that spatial index table only contained GX and GY, or the grid tile identifiers, which required that SDE searched both the index and the table, which potentially increased disk I/O. So by storing all of the envelope values, even though they are redundant, in the index on the spatial index table, it's actually faster to just scan the index by itself instead of scanning the index and the associated table. Now what you can do if you're working with SQL Server is store something called a clustered index for the S table, the spatial index table, when in fact the table and the index are stored as one structure, as Shannon mentioned earlier in the presentation, to avoid the need to store separate indexes and separate tables.
Okay, thank you, Michael. We're going to move on to the last section in the presentation, and that's a little bit longer. We're going to cover a few topics in one. We're going to be looking at ways that you can choose your own spatial index size, and also ways that you can fine-tune the spatial index, how to interpret index statistics and that sort of thing. The first thing we're going to look at here is the defaults that are generated by the ArcGIS software. And I mentioned this earlier in response to a question about whether sometimes the default spatial index wouldn't get built or wouldn't work properly. When you create a brand new empty feature class, it's always going to give you a default of a grid tile size of 1,000, regardless of what your data units are. So if your and remember that the grid tile size is always calculated in data units. So if I create a brand new empty feature class and I want to store data in decimal degrees, I'm still going to have a grid tile size of 1,000, and that's going to represent 1,000 decimal degrees. Seeing as there are only 360 degrees around the circumference of the Earth, that means all of my features will fall in one grid tile. And that initial stage of the query where we try to identify just the features that cross the same grid tile as the query filter, I'm always going to be returning all my features, and I'll still have to search through all the envelopes of all of my features to find out which ones intersect. So there are certain cases where the default settings for a new feature class just aren't going to work. And often you don't really know the size of the features that you're going to be storing, but you'll probably have some idea of whether or not 1,000 comes close to the type of data that you're loading. For instance, if you're storing states in meters, 1,000 meters is going to be far too small of a grid tile. If you're storing large polygon geometry, something like country or state or province boundaries. So that's the default when you create a brand new empty feature class. If you import existing data, it's going to take a look at the data in the shapefile or coverage that you're importing from. It's going to take a sample of your data. It does this because while importing 100 features, it can scan all of them, but if you're importing hundreds of thousands of features, it can take a long time to scan through and analyze every single feature. So if you have more than 1,000 features in your data set, it's going to generate a random sample of these features. So the algorithm isn't checking every feature, and what that can mean is that it may not be an entirely representative sample. You may have some really large features that don't get looked at. You may have a lot of really tiny features that don't get looked at. So it may not really be looking at an average representation of your data. Now, based on the type of data that you're importing, it's got a few different choices for algorithms for calculating a spatial index. If you've got point data, it's going to take a look at the number of points you have and the extent of the data set that you are loading. So the denser the distribution of the points, the more points you have in a smaller amount of space, the smaller the grid tile size it's going to choose. So points don't often come up with a bad default. It's usually on the big side. It's usually larger than they need to be, but points are still sort of okay. When we get to lines, polygons, and multi-point features, it takes a look at the feature envelopes and determines the squareness of those feature envelopes. So it'll come up with a different algorithm if your features are long and thin rather than if the envelopes are more square. Now, again, depending on the sample that it chose, that's what it'll use to pick a spatial index value for you. And because it's a default, defaults aren't always going to work for your data. In fact, there have been occasions where the default that it picked wouldn't allow you to load some of your larger features. So what we're going to try and do next is present you with ways that you can look at your own data and your needs for that data, whether or not that data is going to be changing in the future as well, as a way to start figuring out how you want to calculate your spatial index values. I'm going to take a little stop for another polling question. Now that I've talked about the spatial index default values, I want to know how many of you have created spatial indexes or tried to load data and received some kind of error message telling you that the spatial index was either too small or too large. And based on the answers to this, or rather what we're going to be doing in the next section, is sort of looking at ways that you can avoid getting these error messages. So just a simple yes or no if you've ever received error messages indicating that your spatial index is not the right size for the data that you're trying to load. Now, our goals for establishing our spatial index size is that we want to be able to balance table size and the selectivity of our index so that we reduce the number of I/O operations that we need to incur against the spatial index table. I think Michael pointed out in an answer to a question that usually the I/O is the slowest part of the database server, all the work that the database server has to do. And so if we can reduce the number of I/O operations that we need against or to resolve a query, we'll do a lot to speed things up. Now, what reduces I/O is to reduce the number of records that we need to read through. So we want to make sure that our spatial index table doesn't wind up getting too large. But at the same time, we want to make sure that our index remains selective. And these two are inversely related. And we're going to control the ratio between the two with the grid tile size. So as a rule of thumb, larger tiles, meaning you can have more features that fall completely within a single tile, are going to keep the size of your spatial index table manageable, because you're not going to have a huge number of records that all point to the same feature. But the larger the tiles, the less selective your index is going to be, and the more envelope-on-envelope queries are going to need to be done to reduce the amount of data that gets passed to ArcSDE. So smaller tiles are going to reduce that envelope-on-envelope level query because you're going to have fewer, or rather you're going to have more tiles referencing a single feature. However, that means the size of your spatial index table can grow. And the bigger that table gets, the more data we need to read. So what we want to try and do is establish a balance between the table size and the index selectivity. Okay, I'm going to look at the survey results from that last little poll, and looks like about 47% of you have received these kind of error messages and 53% of you haven't. So the lucky majority. These messages don't indicate that really there's a problem other than that the spatial index is not the right size. So what we're going to try and show you in the next few slides is how to come up with a better size for your spatial index so that you can look forward to not receiving those kind of messages. And this also might explain where those messages are coming from and what you can do about them. Okay, so when we're going to set about choosing a spatial index size, we want to remember that goal, which is to balance the table size and the index selectivity. Now, multi-point, line, and polygon features, we're looking at the feature envelope, not the feature itself. We want to make sure that our features aren't referenced by too many tiles. That's going to reduce the number of entries we have in our S table. So if you take a look at the graphic down at the bottom of the slide, you're going to see two examples of the same two features with different size spatial index grids. In the first example, we only have two spatial index tiles, and we wind up with an S table that has 3 entries. So we're still being selective. If I'm querying and trying to select these two features, I'm not returning a whole lot of additional data with my query. If we look at the other example with much smaller grid tiles, where the grid tiles are definitely smaller than the average feature envelope, our index is very selective, but it's 10 times the size. And if you were to multiply that up by all of your features, you'd wind up with a much larger table. It's taking up more space in your database. It's going to take longer to query. So this is an example of looking at your data, looking at the feature envelopes, and trying to determine a good starting point for a spatial index. And what we figured out is that you definitely don't want to make your spatial index size smaller than your average feature envelope. In fact, you actually want to make it a little bit bigger. Not too much larger than your average feature envelope, but starting at 3 times the average feature envelope is a good starting point. It may not be ideal. Again, everybody's data is different and each data set is different, but it's a good place to start, and it gives you a better idea of what your data looks like. Now, points are different. Points have no area, and neither does their envelope. So the size of our spatial index table is never going to change because our points are never going to cross more than one envelope. No matter how tiny or how large that envelope is, a point feature is only ever going to be referenced once in the spatial index table. So we don't have to worry about controlling the size of the spatial index table, but we still want to make sure that our spatial index table is selective. And again, having all of our points fall into one grid tile is meaning that that first part of our query, that first stage of elimination, isn't really doing anything. And that first stage of elimination should be eliminating the largest number of records. So by reducing the size of our spatial index tiles for point features, we're going to be able to keep our indexes nice and selective. So just sort of a quick review of what we've looked at. We've looked at the defaults that get calculated for you, and if you're going to calculate your own settings or reevaluate the settings for existing spatial indexes, what your goals should be for setting those spatial index sizes, as well as a good starting point for choosing a spatial index size. So I mentioned to you that you want to look at using 3 times your average feature size as a good, or rather your average feature envelope as a good starting point. 3 times your average envelope can be calculated in a few different ways. You can take a look at existing feature classes within your RDBMS and query the envelope values for those features. This information is stored alongside of your features. You can look at the emin_x, emax_x, emin_y, emax_y values and query directly at the database level to get the average extent of an envelope and multiply that by 3. You can use ArcView3x in the query builder. The return extent method with getWidth and getHeight can be used to return the average extent value for a shapefile, and then you multiply that value by 3. The ArcObjects, you can create a macro in ArcObjects, which would apply for ArcView 8, ArcEditor 8, and ArcInfo 8 as well, something that would be executed through ArcCatalog or ArcMap. A little bit long to type the whole thing down here, but you have the iFeature and interface and I believe the iEnvelope or iEnvelope2 interface. You can have methods for the shape properties and getting the envelope of each feature and then the height and width. So the same kind of information is available in all these applications to find out what would be a good starting point of 3 times the average feature size. Now, reporting the spatial index statistics is the next thing that we're going to focus on, and this sort of brings us to the close of our presentation as well. Now that we've taken a look at our goals for calculating a spatial index and establishing 3 times the average feature index, using the index statistics is going to help us understand more about the distribution of our data within the spatial index, and it'll help us fine-tune things. You can start out with 3 times the average feature, and that might work for a lot of your data, but there's probably going to be data that you want to pay a little bit more attention to. Now, this is diving into a lot more database work, and if you've ever done performance tuning at the database level, you know that it's not just something you can do once. You kind of have to play around with a lot of the utilities and learn a lot about how your data gets accessed and that sort of thing. So we're going to go over some of the ways that you can report statistics for your spatial index. The SDE layer command, that's an ArcSDE command. If you execute SDE layer-o SI stats against a feature class, it's going to read and report statistics from the spatial index table. And on the next slide, we'll take a look at the output from that in a bit more detail. At the RDBMS level, you can use trace utilities like SQL Trace or SQL Profiler. You can use these to capture queries that are executed against your data, and then take a closer look at time and I/O statistics that are generated for those queries, as well as the execution path that those queries take. You can query directly into the S table to take a look at the distribution of features per tile. So this is where you take a look to see how many features fell in an individual tile. And that'll give you a pretty good idea of how evenly distributed your features are, or if you have too many features falling in individual grid tiles. Now, I'd like to remind everybody to post questions. We're coming up on a topic review and question and answer section after the following slide, and this will be your last opportunity during this presentation to ask questions. Also wanted to clarify again, we talked about time and I/O statistics. I/O generally refers to input-output, so reading and writing to and from memory or disk. So any statistics that tell you about how many pages were read or how many pages were written to kind of falls under the blanket category of I/O operations. Okay, now we mentioned the SDE layer -o SI stats command, and it sends a lot of records up onto your screen. This is something that you'd execute at the command line in a command window. And it's going to give you a lot of different statistics and ratios and averages and that sort of thing about the distribution of your features and your grid files. Now, the important thing about this command is that you don't want to just look at one of these statistics and try to make estimations of how well your spatial index is performing. You actually want to look at several of these together because each statistic taken out of context can mean completely different things from what it's really meaning for your feature and your grid tiles. So some of the important ones to look at in the top part of the output would be the grid to feature ratio. You want to keep this number as low as possible. Average or maximum features per grid. If your maximum features per grid value is really, really large, it might mean that your spatial index grid tiles are big and they contain far too many features and they're not being all that selective. Percentage of features that are wholly inside one grid tile. If this percentage is really large, that can be a good thing, but it could also mean that all of your features fall inside the same grid tile. So you also want to take a look at the ratio as well as the maximum and average. Now at the bottom of your output, you're going to see record count by group histogram. And this is going to tell you the percentage of features that fall in 4 or fewer tiles, as well as the percentage of features that fall in more than 4 tiles. And we use 4 tiles as a benchmark because a very small feature could cross the boundary of 4 tiles where they intersect. But the minute that that feature envelope crosses more than 4 tiles, you know that it's larger than a tile. And what we want to do here is avoid feature envelopes that are larger than a tile. We want to make sure that our average feature envelope is somewhat smaller than your grid tile size. So just a quick recap of what we've looked at so far in this section is covered a lot of material here. We looked at the defaults and how to generate your own statistics, or rather your own spatial index size, ways to go about choosing and calculating numbers that will help you come up with a spatial index size, as well as some of the statistics that were available to you and how to interpret them. So now we'll have our final question and answer period, and I'll turn this over to Michael for the first question.
Okay, we have a set of related questions from Tricia and Richard that are asking how the spatial index that we're talking about applies to raster data. Now specifically, the grid tile spatial index that Shannon's been discussing is for ArcSDE vector layers or feature classes. But if you look at the structure of the way that ArcSDE raster data is stored, it's although not explicitly indexed like the vector features, it essentially follows the same logic. A unique thing about working with raster data instead of vector data is that the pixels in the ArcSDE rasters are square, and the ArcSDE software can aggregate those pixels into larger squares that we call raster blocks or raster tiles. So essentially those squares of pixels called raster blocks are the equivalent of the feature, the envelope, and the grid tile all stored together. And those raster blocks have a column number and a row number, which is logically equivalent to your X and Y grid tile values. So essentially, logically, the same thing is going on with raster data underneath, though you do not have to explicitly create or manage a spatial index.
Okay, thank you, Michael. We have a question here from Steve. It said, oh, wait, that wasn't the one I wanted to answer. I'll answer that one afterwards. It's a question from Dan that says, what is involved in changing your spatial index for an SDE geodatabase? And this is a really good question, especially if you've got larger feature classes. Changing your spatial index does truncate the spatial index table and completely rebuild it. So if you have a really large spatial index value and most of your features fall in 1 or 2 tiles and you want to shrink that spatial index down, be aware that that could lead to a considerable change in the number of records that you have in your spatial index table. We're going to be truncating that table and rebuilding it. So there's going to be a lot of I/O operations happening at the database level. Every single record that gets reinserted into the spatial index table is going to be logged. So your transaction or archive logs or redo log files, those are all going to be growing, as well as the size of your data files could grow. It's important to make sure that when you're doing this that you have sufficient space to rebuild a spatial index. Similarly, you want to make sure that you're not impacting a lot of users when you do this. When you choose to rebuild the spatial index, you are taking your feature class offline for a little while. And that means that nobody can access that data set until the spatial index has been rebuilt. So because this is a fairly intensive operation, it's probably not something that you really want to be doing all the time for larger data sets. That's why it's useful to understand your data before you start trying to resize it, because if the fewer times you have to rebuild the spatial index, obviously the less amount of resources you're going to be using at the database level. Also, it's relatively easy to rebuild a spatial index for non-versioned data. So data that is read-only within the geodatabase, you simply go to the properties of that data set. So you right-click on your feature class, go to Properties, and click the Indexes tab. The bottom half of the dialog allows you to drop and recreate spatial indexes. You can also use the SDE layer command, SDE layer -o alter, and then you specify a -g option to give it a new spatial index size. So this can be done fairly easily when the data is not versioned. When it is versioned, you kind of have to play a few little tricks by using the SDE layer command to modify the spatial index grid tile and take it in and out of load-only I/O mode. So in any case, you're still taking it offline for your users. And I'll let Michael answer one more question here, and then we'll have to wrap up for this presentation.
We have a question from Robin in Birmingham who's asking if you can build multiple scale-dependent spatial indexes. The answer is no. The ArcSDE server scans the spatial index at every scale. So whether you look at a large number of features or whether you're zoomed way in or doing a small search like in Identify where you click on a feature to return its attributes, the ArcSDE server or Direct Connect driver is always scanning the same spatial index. This does lead into related questions from Michael and Steve, who are asking about indexing feature classes that have different feature sizes. And you may recall from earlier that Shannon was discussing using 3 times the average feature envelope as a guideline for sizing your spatial index. When you have feature classes that contain very small and very large features, ArcSDE will actually allow you to build up to 3 different levels of spatial index tiles, so you can have 3 different sized spatial indexes. The drawback to doing this is that the ArcSDE server needs to scan all of those tile levels for every spatial search, which can adversely impact performance.
Okay, well, it looks like we're out of time, and I think, Steve, we got to that question of yours that I kind of skipped over. I was reading the wrong question up front of me, but I hope that Michael answered that for you. I'd like to thank everyone for participating in today's live training seminar. So on behalf of ESRI, Michael and I would like to thank you, and goodbye.